Okay, thank you very much for a chance to speak here. Yes? Oh, I already have, right? One is enough. Well, most of what I'm going to say is work in progress, I hope so, with my students Kelder Daragival and Dmitry Noszczenko and also Miłosz Panfil, but some things I present are already included in one paper with Markus Toszic and also Miłosz Panfil. And in fact, I will review several other issues. I will start with some review of several topics which probably you heard of, and many of you are expert in those topics much more than myself, so I hope you can support me in case I need support. And also, as the rest of the talk will be work in progress, maybe you would have some suggestions and so on. You will see that maybe I don't have very firm statements or rather conjectures, but hopefully they will soon become more solid. And well, I will start with a very short review of what this A-Polynomial is. Probably you have heard of that. This is some knot invariant, and in fact, the main idea behind this work is not related to knots as such, but rather to those issues related with quivers. But the motivations come from knot invariants, and because this A-Polynomial is some common name, I will very quickly review that. The original definition, which is in fact not the most important one for me, but for completeness, let me just include it. So this original definition is that you consider knot complement in S3, or rather tubular neighborhood of a knot in S3. You look at the fundamental group of that, and you look at representations into SL2C, which you would like to label somehow, or find the moduli space of those representations. And it turns out that they can be nicely mapped into the two numbers, which are not quite arbitrary. So important observation is that the boundary of that is just a torus. So it has two generators, and moreover pi1 of that boundary is z times z. So these generators are called meridian and longitude. And because this pi1 is z times z, when you look at the image of this representation for them, you must be able, at least by conjugation, to put them to a diagonal form with, well, by this I mean some arbitrary element, but this is 0. X inverse, y inverse. So in this way, to a given representation, you can associate two numbers, and moreover, they have to satisfy some relation. So essentially, the space of these representations you can write in the following. Way you get a map into those two numbers. So let's say this is a map from the space of those homomorphisms into C star times C star. And well, this is up to this conjugation. So this is now that this left-hand side, this has to be complex one-dimensional, which means that this x and y, they have to satisfy some relation. Without going into details, this relation can be expressed in terms of an algebraic equation for x and y. And so this is this one complex dimensional object that we obtain, and this is called a polynomial. So this is how it was originally introduced. If I'm right, around 1994, so it's already quite a few years.
Who introduced this?
Well, there is one paper, I'm not sure if I can recall all the names, but the acronyms are CCGLS. One C is for Cooper, someone probably can help me. Cooper, yeah? Yeah, thank you. So that was, well, just very short summary. Just as an example, this polynomial has many nice properties. So for example, it always involves factor y minus 1. And let's say for trefoil knot, it has the following form. It is also important that coefficients are integers. And it has various nice properties. For example, if you replace x by y into inverse of x by y, you obtain the same polynomial up to some monomial factor. Well, I'm not going maybe to review all of these properties, but you can find them, for example, in that paper, at least some of them.
Way of getting it from these representations of
well, from representation we obtain two numbers, but what is important that they cannot be arbitrary, which follows just from this dimensional consideration. So in fact, Thurston showed that the space of those homomorphisms, it has to be 4 complex dimensional, but this conjugation is 3 complex dimensional, so we obtain some 1-dimensional variety, which
the modular space is high dimensional. Its image is 1-dimensional.
yeah. Okay, so, well, this is just a very short review of this original way how a polynomial was introduced, but what is more important for me is that this a polynomial appears in the context of volume conjecture. And also very briefly, without considering all the history and so on, let me just write the following statement in that context. If you consider Color-Jones polynomial, so by this R I mean some integer number which labels different symmetric representations for which you can evaluate generalization of the original Jones polynomial. And as the argument, you take q, which you denote as exponent to some h bar. If you consider the limit where r goes to infinity and h bar to 0 in such a way that q to power r is fixed, then the statement is that it has the following asymptotic expansion. So in this exponent, I have some singular term and then some series in h bar. And in particular, the real part of this S0 is related to the volume of the knot complement. And then this S0 can be obtained as an integral over following one form over a curve which turns out to be the same curve as this A polynomial. And in that context, you also often call this A polynomial just as the classical A polynomial, because there is also its quantum counterpart, which appears in so-called quantum version of the volume conjecture. Which is a statement that those Color-Jones polynomials satisfy certain difference
I'm sorry,
equation.
the classical volume conjecture is this statement over here. What's classical? What's volume conjecture?
Well, it's classical in the sense that the object which
Well, what is the conjecture?
the conjecture is that this S0 you can obtain by the following integral over
Because
a polynomial.
To get the confusion and stuff.
Yeah.
Volume
Volume has to do, I just said it in words, that real part of this S0 is hyperbolic volume of not complement. That's the proper way the volume enters.
Okay. But that identity.
But another aspect of that is that this A polynomial enters here as well. So that's the aspect I'm more interested in. And classical, the word classical appears here because whatever this A classical, well, this A polynomial has to do is with this S0 term. So this is like the leading term in this expansion.
Oh, okay.
Or like the leading, like in semi-classical term you would consider. And the word quantum in this quantum volume conjecture has to do with the fact that it involves not only this leading term, but in a sense all of those quantum corrections altogether. And the way it takes them into account altogether is that the statement of this quantum volume conjecture is that those Color-Jones polynomials satisfy, as I wrote, the difference equation, which I can write in the following way, where this M and L, these are operators which act in the following way. ML acting on JR is just multiplication by Q to power R, and L hat acting on JR or whatever else which depends on R shifts the index by 1. Yeah.
First of all, this is not a volume. This is not a conjecture. It is a theorem. First.
Okay,
Second of all, it's not quantum volume conjecture. There is another conjecture that says that A hat when Q is equal to 1 is equal to A.
That's what I'm going to say, yeah.
That's an AJ conjecture. But that is not a conjecture. What you wrote is a theorem.
Okay, I agree. I'm using maybe a bit older terminology. Okay, so quantum volume conjecture, it will be a statement I will write in a moment. So, okay, so let me start, if you prefer. So there is a theorem that Stavros also contributed to, if I'm right, that indeed this satisfies this difference equation, and you can see that this M and L defined as follows satisfy the Y relation. And then the statement of this conjecture I'm going to write down now is that when you take Q to 1, so it's important that the A hat, it also depends on Q. If you write, this is an operator expression, it depends on M and L, but also Q factors may appear, so let me write them maybe explicitly here. But then when Q goes to 1,
R is an integer or
sorry?
R is a real number?
No, it's integer.
Integer.
R, yeah.
It's kind of for generating series.
This looks like the quantum torus relation.
Yeah, it is. Yeah, sure.
It's actually okay. It's probably better to.
So it reduces to this classical A polynomial whereby X and Y, now I mean whatever you get from M and L when Q goes to 1. Let me write that in this way. Or possibly at least whatever you get in this limit includes a factor like this. Possibly there might be some.
That is called the AJ conjecture. It has nothing to do with the volume conjecture. I don't know why you call it quantum volume conjecture. It's an algebraic conjecture.
Okay, well, as experts, indeed, I was asking for the support, so some people call this volume conjecture. If you don't like, then another name is AJ conjecture, indeed. So let me refer to this as AJ conjecture, and you see, of course, this is from this A and acting on J, giving 0. So But anyway, the main statement of the conjecture is that in the classical limit, this A hat operator reduces to something which involves as a factor this classical A polynomial. All right, so let me say a few remarks, because still this is what I'm presenting now, not of course the main aspect of my work, but some motivation for what I'm going to say in what follows. So one remark is that those A polynomials have been generalized to the case of colored Humphrey polynomials, and then they become dependent on extra variable small a. So they were, this right blackboard have been generalized to that setup, in a sense that if you replaced colored Jones polynomials by colored Humphrey, then everything you get A dependence, but this type of asymptotic expansion still exists, and it can be recovered from some algebraic curve, which is generalization of this classical A polynomial to something that depends on this extra A. However, this left backboard, as far as I am aware, has not been understood in that context, at least along the following lines. But, well, there is this generalization. There is even more general setup where this have been generalized to colored super polynomials, which are certain not invariants which know a bit about the so-called Humphrey homology, and then everything becomes dependent on yet another parameter, small t.
I'm sorry, A hat is A evaluated at N hat and L hat?
No, A hat is operator, which depends on, it's expressed on two different operators and also some variable q.
But you're not going to tell us what it is.
It's well, physically, just think about exponential.
I will write some example, but just operator, something that in...
Remember non-primitive variables.
Let me write, okay, if you like one example related somehow to the unknown, I will comment on that later. But one example, if you want to say explicitly, is the following thing. In fact, a family of examples which depends on some integer f. It has to do with framing of a knot. Sorry, that's so this is some operator expression in ML, and Q factor also appears somewhere here.
Thank you.
So what I mean by this statement is that if you act with this expression on JR, then because of this L to some powers, you get J with different indices. So if here is L to power F, you get J with index R plus F, which then becomes related to other J's and so on. So this is this difference equation.
In your two remarks, so the A dependent is a theorem, the other one is a conjecture.
That's right. Okay, that's one remark. Another one, I already said that, but let me just write explicitly that this A hat knows about all terms Si, in a sense that if you know this difference equation and if you know this expansion, then we can rewrite it as some set of equations for higher and higher coefficients Si. So in that sense, this A hat has all information you need to recover or lose higher S's.
Piotr, it knows about the first derivative. It does not know about the constants.
That's right.
There's an infinite number of constants, which in particular includes the volume conjecture, the actual volume. So if you do WKB on A hat, you produce equations for the first derivatives of the SKs, but not for the SKs themselves. So there is the infinite set of constants that does not know.
Okay, but Piotr, so this is a theorem that if we take this classical A-polynomial, replace it by quantum, and act on this GR, then we get 0.
Yes. Yeah. This is the
Do
theory.
you actually need a volume conjecture in your talk?
No.
This is all. This is some motivation for what I'm.
It's up your top, yeah.
It's not quite what I'm.
It's not theory because it's a huge subject.
Yeah, I agree. I'm a bit sketchy, but I want to motivate some work we are doing now, and I'm not to come maybe into all subtleties that I know mathematicians are very strict about. But indeed, if I write this equation, and of course this difference equation rewritten as equations for this S involves derivatives, because then this become differential equations. So that's why from solving them order by order I get S prime. So of course that's.
How much does A hat know about S?
It knows all the first derivatives
Right.
of all the
Yeah.
SIs.
So this is what A hat knows, but indeed we would like to get this SIs, and now the important remark having to do with the title and the conference here is that those SI, this is in general also a conjecture, can be determined by topological recursion on a polynomial curve. So that's one reason I'm interested in that topic and presenting it here.
Yes, and now that's an important question.
So if you are not familiar with that, probably many of you are, but just to write a few names, it was the first statement like this was made by Digraph and Fuji, and then with Manabe they had some work which almost realized the statement for some simple nodes, but not quite. There were some discrepancies which were later worked out by Gaetan Boro and Bertrand Einard, and there were some other work. I also had a paper with some comments on that with Sergey. So wait.
There are non-perturbative corrections here. I mean, you don't know the Bergman kernel.
Well, I don't want to go into
initial conditions, so you cannot say this statement. It's not true.
what is not true.
Well, we have computed numbers with Boro, aren't they?
For precise choices that depend on the node.
We can discuss that later.
I'm not, as I said, the work I'm doing now is not as such related to nodes, but
It requires
all.
theta function correction,
Yeah,
right?
So
yeah.
such conjecture, another theorem.
It's the conjecture. Yeah.
But important. Okay, so may I ask a question as a physicist?
Well, I'm happy there are a lot of discussions. At least it makes me very happy.
You have x and y, or you have to exponentiate them.
They are exponentiated
So
variables.
it's not algebraic, and the spectral curve is not algebraic.
No, or it is algebraic in this exponential variables.
Now it's not algebraic.
Sure. So as such, it's not.
It's a great. Yeah, what's the problem?
Affiliation.
So what is, I would say, from the point of view of this conference, what is most important here is that this provides one very nice, even though it's conjectural, but very nice application of topological recursion. So you have some problem where some classical algebraic curve arises, or not quite algebraic, but algebraic in exponential variables.
That's even better if it's not algebraic.
Yeah, and it turns out that topological recursion reproduces in some magical way some quantities, which, I mean those SIs, which you know from some other original sources, and well, it shows somehow the power of this recursion. And one way to explain that, well, so please don't comment that much, but but one way to explain that is from the relation to topological string theory. In a sense that there is a way to engineer knots in topological strings in some way by considering certain brane configurations, and then this topological recursion becomes equivalent to so-called B-model computation, which is known to reproduce knot invariants as well. And in this topological string theory, it is in fact crucial to have this A parameter, because this A plays the role of the size of P1 in resolved conival geometry. So let me just make a so-called toric picture. If you are familiar with that, yet more general statement is that you can engineer various knots by engineering different branes in this resolved conifold. So this is toric picture for this resolved conifold, which is some Calabi-Yau manifold, but by different branes, which sometimes in some papers you can see denoted by such extra gadgets in this picture. If they are appropriately engineered, then they encode information about different knots. And in fact, this relation to topological string theory is also very reminiscent to remodeling conjecture. I'm not sure if you can see here on the bottom, so maybe I write here, which is also part of the motivation for what I'm going to say. So the last word of the remark is that by Bouchard, Clem, Marino, and Pasquetti. This is the statement, or even the theorem now, as far as I'm aware, unless you say there are some subtleties. That topological string amplitudes for toric geometries, or toric Calabi-Yau freefolds, are also computed by topological recursion on corresponding mirror curves. So this is another area where you have some, in a sense, naturally arising curve. In this case, this is the mirror curve. you take this formalism of topological recursion, and it turns out that it reproduces quantities which are originally defined in much different way, just in the context of this topological string theory or Gromov-Witten theory. So this all that provides motivations for considering quivers which is this work in progress I am doing now. So let me first say why I am interested in quivers. And I am interested in them because, in a sense, they provide some common generalization of those two setups that I presented here. And they provide this common generalization in the sense that some, well, let's say claim or also physicist conjecture is that if we consider the following generating function, either or of colored not invariants, let's say those colored completely invariants, or very analogously we could consider certain open topological string amplitudes associated to certain branes in more general geometries than this conifold. And then the statement is that we can rewrite those as motivic generating function for some quiver, in fact symmetric quiver, and as I said, we can do that for various families of nodes and also for various branes in those toric Calabi-Gauss. So this is the work which I've been also doing for last 2 years with Markus Reinecke. I mean, we started with Markus and Marko Stosic and my student Piotr Kucharski. And then we have a couple of other papers. Okay, but that's essentially the main statement of that work. And so this ongoing work I am going to present now and I am working on is to try to see that topological recursion also plays a role in that context. But before I comment on topological recursion, I think I should provide some more details just about this statement. So first of all, probably I should tell you what is this motivic generating function. For a quiver, so let me make first a picture to fix some notation. By a quiver I mean, of course, some graph where I have a number of nodes and some positive integers associated to them. Let's say I have m nodes. I think of those integers as dimensions of vector spaces associated to those nodes. So by D, which is a set of those d1, d2, and so on. Well, I refer to such a D as a dimension vector. It turns out, it is not quite obvious, but the quivers which arise in those contexts are symmetric. So this means that if I have an arrow from one node to another, then I must have an arrow in the opposite direction. Those arrows always come in pairs. And such quivers appear both in mathematics and in physics contexts. For mathematicians, these arrows represent maps from these vector spaces associated to nodes, and mathematicians are interested in moduli spaces of those maps and their different topological characteristics, like dimensions of homology spaces and so on. Those dimensions are in particular related to so-called motivic Donaldson-Thomas invariants. For physicists, such quivers also appear. In particular, they encode the structure of so-called supersymmetric quantum mechanics, and in this context of topological strings that I mentioned, this picture of supersymmetric quantum mechanics provides physical interpretation of why those quivers arise.
It's not those that are in cluster algebras.
No.
They are skew symmetric.
Precisely. These are different ones. In particular, I can have also loops here. They are also allowed. And okay, with those little pieces of notation, I can now write what is this motivic generating function. So in general, let me also denote by C the matrix, which encodes the number of those arrows between different nodes. So in particular, Cij is the number of arrows from vertex I to j, and if the quiver is symmetric, it means that this matrix is symmetric. So this motivic generating function, let me denote this as P with index C, because it depends on the quiver or on this matrix. It also involves a number m of generating parameters, and in general, it is given by the following sum, which has very particular structure. I have Q with minus sign, or Q1 half, depends on normalization one uses, raised to the power, which is just quadratic power in those di dj's. In the denominator, I have a number of Q-Poch hammers, m of those, and then this generating parameters raised also to those powers these. So this is this motivic generating function, and it plays different, it has different nice features. One of them, which was at first given by Koncewicz and Seubelman, and then it was proven by Efimov, is that this generating function can be written in the product form, and this product form encodes those motivic Donaldson-Thomas invariants I mentioned earlier. So this product form is in fact a product of quantum dilogarithms. If you fixed some particular descent j, then this product of k to 1 to infinity gives a structure of quantum dilogarithm. So you have here a product of quantum Lie logarithms, and here you get those exponents, which are this motivic dt invariants. So at first they were conjectured by Kontsevich-Seiberman to be integer, and then Efimov proved that they are indeed integer, in fact non-negative integers.
The fixes given T, then J bounded by quadratic bound. Yeah. J is product of J is finite.
Yeah, exactly. Product of J is, for a given D, the product of J is finite. So
Already to be integers in your paper.
Yes, it's positivity.
It's positivity.
yeah, thank you very much. Yeah. Okay, so still I need to be careful. You see that here on the left-hand side I have one x in this generating function, which comes like from not theory problem or topological strings. On the right-hand side, when I just write this motivic generating function, I have a number of x's. So the catch is that those different x's have to be identified in some way to have this equality, and for knots, there is some universal way of identifying those different x's, namely each of xi involves a factor of x, and then a, q, and -1 to certain powers. You can think of this ai, qi, and ti as certain integers, which you also have to specify, but there is a finite number of them. In particular, they are powers which arise in so-called uncolored super polynomial. So this uncolored super polynomial is a generalization of original Humphrey polynomial without any color to something that has just positive signs. It appears in the context of knot homologies. So it is a sum of monomials in A, Q, and T with certain powers. It's finite polynomial, and those powers are the same which appear in this identification. So that's one remark. Another remark is that this statement for physicists is very important because it enables us to prove so-called LMOV conjecture, which appears in two contexts, in the context of knots and also topological strings. And this conjecture is a statement that certain numbers which you obtain from some analogous decomposition into quantum Lie logarithms like this one of topological string amplitudes are integer. And this statement is proven by relating this integer that physicists are interested in to those motivic dt invariants. So this conjecture was postulated around the year 2000. This statement would be proven in general if you would have the proof of this statement. We don't have general proof of that, but we have we can show that for many families of knots, for example. So once we find a quiver for a given knot, then at least for that knot, the integrality of certain infinite set of these VPS numbers is proven by expressing them by these dt invariants. In context of knots, yes. Because these BPS numbers, or these LMOV invariants, in other words, they are like so-called open invariants associated to certain branes. So we have resolved conifold, but some non-trivial brane if you consider some non-trivial knot. Sorry? For symmetric representations, yes.
Yeah.
This is for
symmetric queers appears in the story in two different manners. Symmetric queers producing three Calabi categories with when you get like a Juma varieties or with no relations, which at that moment we just came without any motivation at all. Yeah, so it's another story related to W algebras and blah blah blah. And here, it was really purely calculations. We didn't have.
Well, but
But now there are some restrictions on these quivers.
For algebraic nodes, do you have some collection?
You just
If
take
they
any
algebraic, do
symmetric
you have some
matrix.
collection of curves and the result
Maybe.
conical, and this is just intersection. The quiver is just intersection matrix.
well, I'm not sure if I see that from my perspective, but maybe this is the. I'm not sure if this is the same quiver, because I know you have some work where quivers also
Yes,
arise.
some quivers, but not with
Yeah, yeah.
geometry.
I'm not sure if this would be the same quiver, but okay. Well, I have just 1/4 of the talk, and I still didn't present the main thing. So let me just maybe try to get organized a bit better. Just to show you some example, if you take trefoil knot, then the C matrix, if you have not seen this example yet, takes the following form. So you have 3 nodes and a certain number of arrows. And on the other hand, if you take a quiver just with 1 node, but F loops from this node to itself, so F loops, this is related, I already mentioned that, to the invariance of the unknot. So in this case, this quiver generating function, there is just single parameter x, and this is simply the following generating function. And this quantum operator I wrote before as an example, in fact, is the operator which annihilates this thing. And also important remark, at least for physicists, that those motivic generating function have structure of num-sums. So if for some reason you are interested in num-sums, I think of them in the context of quiver as well.
Piotr, do you have any statement that this function is annihilated by something?
It's obvious. All these functions are tuple and numbers.
Yes, I do, and this is what I'm now going to present. So many of the things I said before is motivation for our work, and what we are doing in the current work is to consider this kind of functions and associating some classical quantum curves to them. So to do that, in fact, we want to identify those x's to have just a single x. And if we choose appropriate quiver, then it makes contact with what I said before, like not invariant or topological strings, but we want to consider such objects in themselves, not necessarily in those other contexts. Yes.
Do you expect eventually that there's going to be some way for any knot to write down what the corresponding quiver is?
Yeah, that is like a dream. So we have a way to find this quiver, but this is kind of computational. And we can do this for knots for which we know, for example, chord conf. But it would be much nicer to start with a picture of a knot and then do some manipulations and, for example, reproduce the quiver. We can't do that at this moment. But still, we have some infinite families of knots. For example, for all rational knots, we know how to find this quiver. Or for some families, infinite families of torus knots, and for all knots up to 6 crossings, including 6 crossings, we know quivers and some other examples. Okay, so our current idea and the work is to consider let me write p of x, which would be this motivic generating function with certain identification of x's. The simplest way you can do that is to just to put all x's to be the same thing. And as Stavros already mentioned, this function is Q-holonomic, so it satisfies some difference equation. Which means that there is some operator, let me write it in this way, which annihilates this generating function. Which also means that, well, there is this Q as well, let me write it. You can also consider the classical limit of this operator. So in this way, we can associate to a given symmetric quiver some algebraic curve, at least once we fix this identification of parameters. And well, this classical curve can also be obtained in some other way, for example, by considering the WKB approximation of this sum. That's one way to consider that, or yet another way is to define this y as a kind of classical limit of this operator y hat. Well, I should have mentioned here that in this context, if this is a generating function, then this x acting on p of x is just multiplication by x, but y acting on p of x is shifting the argument of this p by q. So here you can see that y and x satisfy, well, also this quantum torus relation. So by this classical limit of this y operator, I mean the following ratio when q goes to 1. And I need to divide here because in the leading order, if I take q to 1, which means h bar to 0, then this function has similar singular behavior, but in this ratio, the singularities cancel. And from that, I obtain just some function of x, which it turns out satisfies some algebraic equation, which is the same equation which I get in this limit. So here the situation is quite analogous to what I presented in the beginning of the talk for knots. We have some large set of interesting Q series. We can associate to them various classical or quantum curves. And now the statement we want to give, or at least to understand as much as possible, is to show that the relation between this classical curves and these quantum operators can be also captured by the topological recursion. So these curves A of xy, they are also algebraic but in exponential variables.
Possible to call x, y, and some many variables. It's with some bunch of equations. Implicitly, one can say what are points x and y sitting on this curve without writing polynomial. X and y and some maybe variables x1, or whatever at this point, and maybe some other variables. So it's with some bunch of very explicit equations.
Yeah, well, I mean before identifying x's.
Oh, yeah.
Yes. Yeah. So then I can also, well, in fact, this identifying them means that I have to eliminate some variables from the set of equations, and then I get.
And this is Lagrangian operation, so we assume that x's are commuting variables.
Yes. Here they are coming. Yeah.
First of all, linear it's a rank 1 model.
So it turns out that this P of x also has analogous expansion as I wrote in the beginning, and then our claim or conjecture is that those SI terms can be determined by topological recursion. So this is like analogous to this removal conjecture or the statement for knots. And what is nice here, of course, well, we don't have general proof. It seems quite hard. But what is nice here is that there are lots of quivers, of course, so we can generate very large number of examples where this classical curves have genus 0 or maybe 1. So we can do really kind of simple topological recursion calculations. The difficulty, for example, with knots or in general with topological strings is that those A-polynomials or mirror curves in general have higher genus, so it's hard to do explicit calculations. But here we can generate many examples where curves have low genus, so it provides a large zoo where we can explicitly test such statements. And if we can generate this SI by topological recursion, then we can also generate this A hat just over by order from the knowledge of SIs. So again, a few remarks. I already
Piotr, you
Yes.
consider that a polynomial, classical a polynomial is given.
Well, I start with a quiver, and to that quiver I associate this, what I call a polynomial for quiver. So this object that appeared in the title, this one, I should write it because this was in the title. So, and the word the name a polynomial is just by analogy with knots or whatever else people considered before. Yes, so I'm just finishing. So I just write some remarks, and if I have 1 minute remaining, maybe I just write some one example. So we have large number of examples with genus 0 or 1, so we can do really explicit calculations. One of the hopes that we have by applying that topological recursion is to show that because this P of x, of course, captures the motivic dt invariants, This means that this topological recursion could reproduce at least some of them which are preserved in taking this identification. Or you could reverse the statement and ask what constraints on topological recursion are imposed by the fact that this generating function have in fact some peculiar structure which is captured by those integralities. Okay, and well, I haven't written it yet. I'm not sure if it was written in this conference, so maybe I should clarify that at least very briefly. That by being determined by topological recursion, I mean that we want to identify this P of x with the following. I already wrote that, so I don't need it. But I mean that those different SKs which appear in this series have the structure which follows from the wave function interpretation that appeared also in some other contexts. So I take omega GNs and integrate them in appropriate limits and take appropriate combinations. For omega Gn, I take GNN such that they satisfy the following relation, where k is the index here. This is for k at least 2. And then S0 is what it was before. And S1 is given by yet another formula. It's essentially related to the integral of omega 2. So by this topological recursion, I mean that we compute this omega Gn for this Quiver A polynomial, and then we reproduce those SIs in that series. And yeah, it seems I wanted to give some examples, but well, maybe I already gave one, the simplest one related to this one vertex Quiver, but you could see how it works. In that context, the results are not new because they in essence reproduce what people did for BKMP conjecture, but this is also the same computation for Quivers, and then you can do analogous things for other Quivers. I think I have to stop. Thank you.
So let's thank Is there any other question? I have one. First, when you write that, you don't put the theta terms, so I guess this is for genus 0 curves. Do you need the theta terms? I guess so.
Well, so far we just made computations for genus 0 curves, so I suppose I would need similarly as you.
If you want it to work for, let's say, the figure 8 knots, you have to put them.
Sure, yeah.
Know what you said, you knew these motivic generating functions for certain classes of knots.
Yes.
Do you know them, for instance, in these knots that you get from, for lack of a better word, we'll call them alternating braid knots. So you take a braid with some certain alternation conditions on the crossings and you make a knot out of it.
So I'm not sure which conditions you mean. I can tell you for which knots we know those. Quivers, so for all knots which have at least 6 crossings, and for example for 6-2 or 6-3 nodes, those quivers have 11 or 13 nodes, so they are quite big matrices already.
I'm talking about it.
Well, so I'm not sure which class you. I suppose some nodes from the class that you mentioned are some of those. So for all twist nodes, 2, p and 3, p torus nodes, and all rational nodes, which are associated to all rational numbers. For those nodes, we know those corresponding quivers. So some of them probably include those that you
So let's thank Piotr again.